Welcome everybody to today's episode of One Universe News, where we'll be learning the same old stuff in which we always learn, whether it's about the time I danced in my room last night, wow. So, anyways, for today's episode of One Universe News, we'll be discussing even more chemistry. Yeah, I know you might be getting tired of this kind of stuff, but there is so much to chemistry to tell about, it's kind of hard to stray away from it. Anyways, let us get started. So, everybody knows about the atom being what makes up virtually everything in the universe. You know, it makes up the sun, the earth, the moon, the oceans, my hand, it makes up everything. And everybody knows about how it consists of the common baryons, the proton and the neutron, and the most common lepton, the electron. If not, let us just give a brief review. Protons and neutrons make up the atomic mass, are in the center, orbited by electrons, yada, yada, yada. Search Google to find out more. Okay, so, considering that you already know about those subatomic particles now, what exactly is there to find out more? Well, what if I were to tell you that there were more subatomic particles than just those? Yeah. Mind blown. Well, actually, I hope your mind doesn't blow, because I don't want to be there to clean up your mess after your brain explodes. Just saying. I'm on a schedule here. Anyways, so, I just said that the nucleons, the neutrons and the protons, are baryons, while the electron is a lepton. Well, the lepton is basically its simplest form. We can't go much farther with that until I explain to you more about that, so let's get back to leptons later. To start off with, you might as well be told about this certain subatomic particle known as a quark. Predicted in 1964 and discovered by the Stanford Linear Accelerator Center in 1968, the quark is essentially an elementary particle in which happens to make up baryons, made of 3 quarks, and mesons, which are created by 2 quarks. Basically, quarks are categorized into 6 categories: the up and down quarks, the charm and strange quarks, and the top and bottom quarks. That may sound like the strangest thing ever, but that is literally what they are named as. Up, charm, and top quarks have an electrical charge of positive 2/3, while down, strange, and bottom quarks have an electrical charge of negative 1/3. Protons consist of 2 up quarks and 1 down quark to make an electrical charge of positive 1, and neutrons consist of 1 up quark and 2 down quarks to make no electrical charge. The strong nuclear force bonds all of these using these small particles called gluons, in which keeps them all tight and close together by using their color charge. The color charge, which is different from their electrical charge, is simply either red, blue, or green. They aren't actually red, blue or green, it is simply how the scientists labeled them, especially on diagrams to set a distinction. Anyways, the 3 quarks bonded together by the miniature gluons, or otherwise, the strong nuclear force, creates a baryon. Now, essentially, things may get a bit more complicated as I keep on describing more and more subatomic particles into this, so therefore, the standard model for subatomic particles should be useful. It tells all of the subatomic elementary particles in which, at this point, has so far been discovered, including the baryons, mesons, and the leptons. Another thing to note is that the universe is made up of 4 elements. No, not the Avatar elements. Why did we even bring that up anyway? I mean, the universe is made up of 4 different elemental forces at its base within particle physics, which are the strong nuclear force, the weak nuclear force, the gravitational force, and the electromagnetic force. I already demonstrated an example of the strong nuclear force. It is what keeps elementary particles together. It is the strongest force in the universe, but it is also the shortest in range, and the electromagnetic force can often repel different particles from fusing and attaching to another particle with the strong nuclear force by having the electromagnetic force push it away before it gets into range. This is why you don't see everything mixing with each other in order to become some ultra-mega black hole. Meanwhile, the weak nuclear force is responsible for radioactive decay, explained in our 11th episode of One Universe News, and allows nuclear fission to happen, which is essentially 2 particles previously fused with each other broken apart from each other. Finally, the gravitational force is self-explanatory. It's what causes gravity, proportionate to a rise of mass. Knowing the 4 forces in particles, we can continue. Mesons are made up of 2 quarks, as described earlier. The most common example is a pion, made of a quark and its respective antiquark. Essentially, the antiquark of a quark isn't straight-up antimatter that can make up some whole universe of antimatter or anything like that. It is only the opposing matter to the actual object itself. Thus, an antiquark can cause a heavy reaction on its twin, the quark, but won't cause some massive explosion to occur elsewhere. It is not actual antimatter, which, at this time period, is still theoretical. The antiquark and the quark form a pion, which is simply there just to act as the strong nuclear force agent for nucleons, similar to how gluons do the same thing between quarks. Note that most of these subatomic particles are also very unstable and can usually last for only a couple nanoseconds. There are also lots of other subatomic particles we won't be getting to today, but I don't think I want to be here to explain to you in a 50-minute video about every single individual subatomic particle. So, anyways, other ones on the standard model of particle physics are the muon and the tau, which happens to be very similar to electrons. In fact, you can practically say that they're fat electrons, since the muon is over 200 times heavier than the electron and the tau is about 3,500 times heavier than the electron. Phew, they need to stop eating Big Macs every day. Even so, the muon and the tau have many mysteries clouding around them. It is still unknown as to what they're used for in subatomic particles. Some scientists even predict that they might be what reveals another particle physics force not yet uncovered, like the weak and strong nuclears with the gravitational and electromagnetic forces. All we know so far, though, is that they're highly unstable and are usually only formed when fusion is occurring, such as in a particle accelerator or at a massive shower of gamma rays. Along with that, but they also have their respective neutrinos. According to the law of conservation of mass energy, when particles decay, they still result in new subatomic particles. Often, when the muon and tau decay, along with the electron, the three subatomic particles can create several different possibilities for radioactive decay, and this includes the respective neutrinos. They aren't relatively used for anything too special, they're just neutrinos. Right now, they are also still being studied, which is very difficult to do with them. They travel nearly at the speed of light and they don't have any electrical charge, causing it to be hard to detect and study them. Finally, the bosons exist, which contain the already explained gluon, the photon, the Z and W bosons, and the Higgs boson. The photon is the simplest, it is simply a particle of light. A photon literally is light. Without it, there would be no light. Basically, every single light you see is caused by photons being made and being driven by rays of light, thus creating light in the first place. That is a photon's purpose, it creates light. Hence as to why it has no mass, no electrical charge, and just your average spin of one. The Higgs boson is next. So far, scientists still have yet to study it. The Higgs was discovered only back in the year 2013. But many people believe it is what gives all matter its mass in the first place, and without it, this universe wouldn't be able to function, for it doesn't have the Higgs to give all matter its mass. That is still just a theory, after all. Finally, we have the Z and W bosons, which are both simply responsible for creating the weak nuclear force in the first place. Without them, we wouldn't have the physics to have radioactive decay, which would cause fission to be impossible, thus rendering several events in the universe to not be able to occur and possible changing physics itself to where the universe isn't functional anymore. That is a basic summary on some of the subatomic particles within our universe. Stay tuned next time for more One Universe news. For now, check out more videos later on.